Welcome back to Intelligent Survival. Right now, the machines we depend on every day are quietly aging in ways most people never notice until it's too late. Modern engines are more advanced than anything in history, yet they are also more sensitive, more precise, and in many cases, more vulnerable. The cost of replacing them has climbed to staggering levels, and yet the knowledge needed to extend their lifespan is rarely discussed outside specialist circles. This isn't about secret hacks or miracle fixes. It's about understanding a problem engineers identified decades ago and applying a solution that has been refined through war, industry, and relentless scientific testing. What you're about to learn is not theory. It's grounded in real history, real chemistry, and real-world survival thinking. Because when your vehicle fails, especially in remote or higher-risk environments, it stops being an inconvenience and becomes a genuine threat. The hidden battlefield inside your engine determines how long it survives. Your engine may look like a perfectly machined piece of metal, but at the microscopic level, it is anything but smooth. Every surface inside it is covered in tiny peaks and valleys. When parts move, these rough edges grind against each other at high speeds. Oil is supposed to keep these surfaces separated, creating a protective layer that prevents direct contact. When that layer is strong, the engine operates efficiently and with minimal wear. But there are critical moments when that protection breaks down. Cold starts, for example, are among the most damaging events in engine experiences. Oil settles when the engine is off, and when you start it again, there is a delay before proper lubrication is restored. During that time, metal is scraping against metal. This same vulnerability appears in stop-and-go traffic, heavy acceleration, and high-temperature idling. In these moments, the protective oil film becomes too thin to fully separate moving parts. Engineers call this boundary lubrication, and it is responsible for the majority of long-term engine wear. This is not speculation. It has been consistently observed in laboratory testing and real-world engine analysis. The harsh truth is that most engines don't wear out gradually during smooth highway driving. They degrade during the exact conditions people experience every day. A survival solution first discovered in wartime aviation changed everything. Long before modern consumer vehicles existed, engineers were solving life-or-death problems in military aircraft. During early aerial combat, engine damage often meant oil loss. Without lubrication, engines would seize quickly, leaving pilots stranded in the air. To address this, researchers turned to a naturally occurring compound with remarkable properties. This material could bond to metal surfaces and continue reducing friction even when oil was no longer present. It acted as a last line of defense, giving pilots precious extra minutes to return to safety. This discovery wasn't about improving efficiency or extending maintenance intervals. It was about survival under extreme conditions. After the war, the same principles began to appear in industrial applications, where machinery operated under constant stress. Over time, the technology evolved from crude suspensions into highly refined chemical solutions designed for modern engines. The breakthrough came when scientists learned how to make protection activate only when needed. Early attempts involved mixing solid particles into oil, but these had limitations. They could settle, clog, or fail to reach critical areas. The real advancement came with the development of oil-soluble compounds that could travel seamlessly through the lubrication system. These compounds remain inactive under normal conditions, but when heat and pressure spike, exactly when metal surfaces are about to make damaging contact, they undergo a chemical reaction. At that moment, they form an ultra-thin protective layer directly on the metal. This process is triggered by friction itself. In other words, the very conditions that cause wear also activate the defense mechanism. This is one of the most efficient forms of protection ever developed because it doesn't waste resources coating every surface all the time. It responds precisely where and when it is needed most. Laboratory data has shown that this approach can significantly reduce friction under extreme conditions. While real-world results vary, the overall impact is clear. Less friction during critical moments leads to less wear over time. This is not a one-time fix. It is an ongoing process that continuously reinforces protection as the engine operates. The reason most drivers never hear about this comes down to economics, not secrecy. There is no hidden conspiracy preventing this knowledge from spreading. The reality is more practical and, in some ways, more frustrating. These compounds are not sold as standalone consumer brands with massive marketing budgets. They are ingredients supplied by chemical companies to oil manufacturers. When you buy a high-quality engine oil, you are often already getting some level of this technology, but it is rarely highlighted. Oil companies focus on branding complete products, not educating consumers about the chemistry behind them. There is little financial incentive to explain the details of additive packages when most buyers are making decisions based on viscosity and brand recognition. At the same time, earlier versions of these compounds had to be reformulated to meet emission standards, which slowed their widespread adoption. Modern versions are fully compatible with today's engines, but the gap between industry knowledge and public awareness has remained. In high-stakes environments, this knowledge is already standard practice. Industries that rely on equipment for survival or profit do not ignore friction reduction. Heavy machinery operators, marine engineers, and long-distance fleet managers all understand the importance of minimizing wear. In some regions, taxi fleets routinely push their vehicles far beyond the mileage most private owners consider acceptable. Their advantage is not luck. It is disciplined maintenance using oils and additives designed to reduce friction at a microscopic level. When a machine's failure has immediate consequences, there is no room for guesswork. The same principles apply to anyone who depends on their vehicle in remote areas. During long-distance travel, or in situations where breakdowns carry real risk, understanding what this technology can and cannot do keeps expectations realistic. It is important to stay grounded. These compounds do not make engines indestructible. They cannot repair existing mechanical damage or reverse severe wear. If an engine is already failing, no additive will bring it back to life. What they can do is reduce the rate of wear moving forward. They are most effective when used consistently in engines that are still in good condition. They also do not replace proper maintenance. Oil changes, correct viscosity, and manufacturer specifications still matter. This technology works as part of a system, not as a shortcut. There are also specific cases where friction reduction can cause problems, such as in certain motorcycle engines that rely on friction for clutch operation. So understanding your machine is essential before making any changes. Applying this knowledge in a practical way can extend engine life significantly. There are two straightforward approaches. The first is selecting high-quality engine oils that already include advanced friction modifiers. This requires reading technical data rather than relying on marketing labels. The second approach involves using a dedicated additive designed to provide this type of protection. Application is simple and fits into normal maintenance routines. The additive is introduced during an oil change and works continuously as the engine operates. Over time, the protective layer forms and reforms, smoothing microscopic imperfections and reducing wear. The cost is relatively low compared to the potential savings in extended engine life. This is not about chasing perfection. It is about reducing cumulative damage over thousands of cycles. Small improvements applied consistently can make a measurable difference in how long an engine remains reliable. There is also a lesser-known method for addressing one common engine issue before it becomes serious. In modern engines, piston rings are designed to minimize friction, but this makes them more vulnerable to carbon buildup. Short trips and low operating temperatures allow deposits to accumulate, causing the rings to stick. When this happens, oil can slip into the combustion chamber, leading to increased consumption. Before assuming the worst, there is a simple method worth trying. Running the engine at sustained higher speeds under load can generate enough heat and pressure to break down these deposits. This technique has been used by mechanics for decades. While it does not always work, it can resolve issues without costly repairs if the problem is caused by buildup rather than mechanical failure. The real lesson here is not just about engines, but about awareness. Throughout history, some of the most valuable technologies have not been hidden. They have simply been overlooked. The knowledge exists, documented and tested, yet rarely communicated in a way that reaches everyday users. The gap is not access, it is attention. Your engine does not fail because time runs out. It fails because of countless small moments where protection is insufficient. Cold starts, traffic, stress, these are the true enemies. Reducing their impact is one of the most effective ways to extend the life of any machine you depend on. If this kind of practical, history-backed survival knowledge matters to you, subscribe to Intelligent Survival and share this with someone who relies on their vehicle every day. The difference between breakdown and reliability often comes down to what you know and what you choose to do with it.